Dear friends, today my topic is harmonic oscillator. You know very well what we mean by oscillator. Oscillator means anything which is oscillating to and fro about a fixed point. This is fixed point. And anything which is oscillating like main to extreme, extreme to another extreme, and then back to the main position. Okay. Now, potential energy, when anything, any particle, any atom, which is executing SHM, it moves from mean to the extreme position, then potential energy starts increasing. And the formula for potential energy is half kx square, where what is k? This is force constant. As x increases, potential energy gone increasing. So if I draw a graph, now I'm discussing first of all classical viewpoint. According to classical viewpoint, okay, the variation of potential energy, it is according to this curve. Okay, so potential energy is maximum here at the extreme position, half kx square. Then at the main position, potential energy is 0. At the another extreme position, it is again half kx square. Differential equation of the SHM, and it may be written as k upon m, dimension wise the value of k upon m and omega square, it is the same. So this is the differential equation, d2x over dt square plus omega square x equals to 0, where omega is root of k over m. Now what is the solution of this equation? Very simple. It is because simple harmonic motion, so sine function or the cos function, x equals to a sine omega t plus phi, where phi is the initial phase at time t equals to 0. So this is the solution. I mean, we are having differential equation. We are having the solution, from classical point of view. Okay. Meanwhile, the conservation of energy. When potential energy is maximum, kinetic will be 0. When potential energy is 0, okay, kinetic energy will be maximum. So this is the graph of kinetic energy. Now, what about the total energy? It remains constant. And total energy is half kx square, where x is what? The amplitude. Okay, if amplitude is A, then total energy becomes half Ka square. Very important relation. Classical physics says the energy E may have any value depending upon the A. Mean E energy, it is continuous. Mean because A is continuous, choose any value of A, you will get E. This is the classical viewpoint. But it is not true experimentally in the microscopic bodies like atoms when they oscillate. So we have to think the harmonic oscillator from quantum physics. Because A having any value, so classical viewpoint is total energy having the continuous values. Now we are coming on the quantum viewpoint. We are writing Schrödinger equation, time independent. Substituting the value of potential energy here, half kx square. So the differential equation becomes like this. We know the value of omega. Substituting the value of k here. Okay. So this is the differential equation, Schrödinger equation. Now to solve the above equation, we are making some substitutions just to solve this equation. Very important substitutions. First of all, alpha, very, very important. Remember always. And it is the assumption, let m omega over h cross alpha, let 2m e upon h cross square is beta. So these are the two assumptions or the substitutions. Open the bracket, Schrödinger equation. Now substituting for alpha and beta. Substituting for alpha and beta. So the equation reduces to. Now this is the equation. Okay. Now one thing is very important. What are the dimension of alpha? So the dimension of alpha, it is L raised to power minus 2. Now we are making another substitution, a variable y, dimensionless variable, very important. We are going to make a dimensionless variable y with the help of alpha, because we know very well alpha having the dimension of L minus 2. And how we do that? Y is equals to let under root alpha x. Under root alpha x mean now L raised to power minus 2 and root and L. So y becomes dimensionless. So the y is variable which is dimensionless. Y is root of alpha into x. So let me write the d psi by dx. So let me write d psi by dx. D psi is here, dx is here, and multiply and divide this by dy. So d psi by dx may be written as like this, differentiating it with respect to x. So dy by dx becomes only root of alpha. Okay. Now substituting this value, here. So this is clear. Now again differentiating once again with respect to x. Right. So d2 psi by dx square. Now look. This d, it is here. Okay. And then this dx, it is here. Then d psi by dy, it is here. And root of alpha, it is here. Okay. Now what we do then? We multiply and divide by dy. Okay. Multiply and divide by dy. So now the equation is now look, dy by dx is root of alpha, substituting it here, and we are already having root alpha. So root alpha becomes alpha. So alpha, so equation becomes, now we are getting this equation. So very simple, squaring both sides and finding the value of alpha. Now already just proved, okay, just proved, see the above slide, previous slide, where I proved already d2 psi by dx square is alpha d2 psi by dy square. Okay. Then instead of writing this, we substitute this value. Substituting for, alpha square x square. Now dividing each term by alpha. Now from here alpha x square is equals to y square. So equation reduces to this one. Now we are making an assumption because our problem is finding the solution of this equation. This is a very important question. What will be the solution of this equation? And it's somewhat difficult. So we are making an assumption. Y is very, very, very large. So beta upon alpha neglected. This is very simple differential equation. Now only when the v tends to infinity, and the solution of this equation is y is equals to e raised to power minus y square upon 2. This is a solution because if you differentiate it with respect to y once, then twice, then you will find this value and numerically this value, they becomes equal, and minus mean then becomes 0. So psi is the true solution, but only at condition when y tends to infinity, otherwise no. So this is a conditional solution, and this condition is called asymptotic solution because y tends to infinity, not for always. But we need a general solution of this equation. Okay, we need a general solution. This is the general. We take the help from the asymptotic solution for general solution. So we are writing psi is equals to a e raised to power minus y square over 2 into h some function of y. Okay, from asymptotic solution to we are coming to the true solution of this equation. But the problem is we don't know what is h. H is unknown here. And then now problem becomes, because psi is the true solution, but we don't know h. So problem comes here, how we find the value of h. Okay. The problem, what is h? Now differentiating it with respect to y. Now keep in mind there are two functions. Okay, this one and this one. So there's a product rule. One function differentiation of second and second function differentiation of first. So we are having two terms, very simple differentiation. Now again differentiating. Now keep in mind here, now we are having three functions, 1, 2 and 3. So we will have now three terms here. Now here we are having two functions. So we will have two terms here. Total term becomes 5. Very simple differentiation. There are three functions. You do it yourself without copying it from the video, because simple mathematics, the product rule. We are having the 5 terms total. Okay, now combining the two terms then becomes 4. Okay, now 4 terms. Now this is common from the 4 terms. Okay. Now our basic equation was this one. Okay. Now substituting this value d2 psi by dy square here in the basic equation. Already you go to my previous slide in the video. And also psi substituting here. So the equation reduces to. Substituting psi also. Now just do the simplification. Very simple. Now we're coming to this equation. Now here, this equation will give us the value of h, but there is one condition. Okay, because the problem was, this was the solution, okay. The problem was, what is this h? So we build an equation for finding h, and that is this equation. But what about this equation? What the value of h is from this equation? Now, okay, this differential equation will give us the value of h only at one condition, if beta upon alpha equals to 2n plus 1. If beta upon alpha equals to not equals to 2n plus 1, it is not possible for finding the value of h. We can find h only if beta upon alpha is 2n plus 1. Now n equal to 0, 1, 2, 3 and so on. Okay, this equation will give. Now what is beta and what is alpha? Now dividing the two, substituting in our equation in the condition and finding the value of E. Very, very, very important. We are getting the energy of harmonic oscillator. But the quantum mechanics tells us energy is not continuous. This is the energy of simple harmonic oscillator. But, very important is this is the energy, and when you put n equal to 0, that will be the least energy in quantum mechanics, and that least energy is called 0 point energy. And how much that it is? 1 by 2 h cross omega. When you put n equal to 1, you will get second energy. N equal to 2, then third energy. Energies are discrete, not continuous. And there is a gap between the two energies. And what is that gap? That gap is h cross omega. So this is different from classical physics. Classical theory says any energy, not discrete. Quantum says energies are discrete. Okay? Thank you.